Due to geographical and dam design constraints, hydropower accounts for only about 20% of all electricity produced globally. Currently, hydropower dam is not widely deployed due to the difficulty of selecting suitable dam sites, huge capital fund involved, long duration to build, and a growing concern is the effects on the local ecology. A solution is to build hydroelectric inflow dams, which are scalable according to electricity demand and available fund. Such hydroelectric inflow dams are located in a body of water or located along water shorelines to harness renewable potential energy. The present invention describes a hydroelectric inflow dam system. Water flowing into the inflow dam is operable to continuously rotate a turbine and a generator to produce electric power. An implementation is locating the inflow dams in a body of water or along a shoreline of a sea, river, reservoir, lake, lagoon, and so on. The inflow dam is built higher than the highest water level, but the walls of the inflow dam are formed with nozzles so that jets of water flow from outside the inflow dam into the interior cavity. The kinetic energy in the water jets is imparted to the impellers of an impulse turbine, thereby rotates the impulse turbine to generate electric power. The water downstream of the turbine flows into a water-holding intake valve chamber, and the releasing of water is controlled by spring-actuated balls and a slidable valve plate. The regulated intake valve chamber has one or more air release ports to reduce impeded flow of water into the air chamber. When the valve plate is in a closed position, all the holes of the intake ports are sealed and occupied by the spring-actuated balls. Water aft of the turbine fluctuates periodically between high and low levels. When the water level in the intake valve chamber reaches a high level and activates a float switch, which then triggers the control valves to retract back the spring-actuated balls to its open position and allow water to flow into the air chamber. After a periodic time interval, the spring-actuated balls are moved back into the closed position. An air displacement control valve is used to periodically control compressed air supply into the air chamber and to periodically displace water from the air chamber through a plurality of one-way discharge flap valve, through which water is discharged out and any water tending to flow in would close the flip valve. With continuous charging of water inside the inflow dam, rotation of the turbine is non-interrupted and electric power generation is continuous. The inflow dam is located along a coastline. It is possible to locate the inflow dam a distance inland from the coastline. With this variation, it is possible to lower the costs of constructing the inflow dam along the coastline, or to minimize any adverse environmental impact. Adjoining each inflow dam is a substation where the outputs of the generators and solar panels or wind turbines are coupled to the external electric grid. An advantage of the inflow dam system is that it is scalable in terms of power capacity, number of units of inflow dams, and available funds. The power generation capacity in turn depends on demand for electric power. For example, when there is high electric power demand, more inflow dams can be added after some initial installations. Some of the inflow dams can be closed by regulating the intake sleeves for preventive maintenance or when electric power demand is low. It is also possible to implement the inflow dam system from a microsystem of a few kilowatt, a mini system of a few hundred kilowatt, to a large-scale system of several megawatt capacities, which conventional hydroelectric dam system is not scalable. Obviously, inflow dams have many advantages over conventional hydro dams. They can be deployed widely and are able to cut down carbon emission tremendously. If we can harness clean, renewable power, you can solve almost everything.